Again, welcome to the students. So we were discussing the properties of the matrices, and property 1 that we have already discussed, which simply refers what? That is, the matrix multiplication is not commutative in general. It may not be commutative. Now we will continue in the same direction. Look at here. Commutativity of matrix multiplication does not hold even if AB and BA are defined and also of the same order. In the last example, what we did, we have taken two matrices A and B. In this case, AB was possible and BA was also possible. But the order of AB and BA both were different, right? They are not of the same order. So in this direction, what we will show in this example, AB exists, BA exists, and their orders are also same. Even then they are not equal. Are you getting the point? The difference between this example and the last example is what? In the last example, we have taken two matrices A and B. Their product AB is possible and BA is possible, but they are of the different order, so they cannot be equal. But here in this example, we will take two matrices A and B. AB is possible, BA is possible, and the order of AB and order of BA both are same. Even then, AB is not equals to BA, right? See, let us consider the two matrices A and B as follows. This is your matrix A and this is your matrix B, right? See, A is a 2 by 2 matrix and B is also 2 by 2 matrix. So, naturally, both are square matrices. AB is possible and BA is possible. And the order of AB will be 2 by 2 and order of BA will be 2 by 2. Means the resultant product AB as well as BA both will be of the same order, right? See, what is AB? AB is this. This is A, this is B. You should try to multiply these matrices yourself so that you may excel in the process of multiplication. This is A, this is B. If we multiply these two, we get the matrix this, right? Now, the order is just reverse. Find out BA. This is B, this is A, and if we multiply these two, we will get the product BA. Now see, the order of AB is 2 by 2 and order of BA is 2 by 2, right? The resultant product, both are of the same order, that is 2 by 2, but even then AB is 0, 1, minus 1, 0, and BA is 0, minus 1, 1, 0. Even then AB is not equals to BA. Thus, AB and BA are of the same order, but AB is not equals to BA. This shows that commutative law does not hold good in case of matrix multiplication, right? Now, I have given you many examples in which AB is not equals to BA in the last few slides or even in this slide. AB is not equals to BA. Now let us give you a simple example in which AB and BA both exist, even then they are equal, right? See, this is an example where AB is equals to BA. Say, let A is this and B is this. Now find out the product AB. Let us give me one case AB. BA you can find yourself. AB is what? 1, 2, 2, 5, this is A, and B is what? 5, minus 2, and 1, right? So the product AB is what? See, take the first row of the first matrix, multiply it with the first column of the second matrix. 1 into 5, that is 5. 2 into 2 minus 4, that is 5 minus 4, right? Multiply the first row with the second column. 1 into 2 is minus 2 and 2 into 1 is plus 2, right? Now, take the second row of the matrix A. Multiply it with the first column. 2 into 5 is equals to 10. 5 into minus 2, this is equals to 10. Now, the second row should be multiplied with the second column. 2 into minus 2 is minus 4. And 5 into 1 is plus 5. So what you will get, the product AB is 5 minus 4 is 1, 10 minus 10 is 0, minus 2 plus 2 is also 0, and minus 4 plus 5, this is 1. Oh, this is the same. So we are getting the product AB. What is this? Can you identify this? This is an identity matrix of order 2, 1, 0, 0, 1. Likewise, you can find out the product BA, and fortunately, BA is also coming out to be an identity matrix. Therefore, AB and BA both are same, right? Are you getting the point? So all the cases AB is different from BA as well as AB is equals to BA. So you can think that if AB is equals to BA, then why matrix multiplication is not commutative? It's a natural question. As I have told you just few minutes earlier, a property is said to be satisfied if it must satisfy in all conditions. If you are having even a single example which does not satisfy that particular property, then we can't say that the property is satisfied. Are you getting the point? What does it mean? It means if you take two matrices, then A plus B is equals to B plus A always, right? A plus B is equals to B plus A always. You cannot give even a single example of two matrices in which A plus B is not equals to B. That is why we say that the matrix addition is commutative. But here we have a number of examples. I have shown you many examples in which AB is not equals to BA. Are you getting the difference? If AB is not equals to BA, it shows that commutativity does not hold good in case of matrix multiplication. Hope you understand the difference. Property 2, if A, B and C are three matrices of order M by N, N by P and P by Q respectively, then A, B, C is equals to this. You know, this is what we have already discussed, this property in case of addition. That was what? A plus B is added to a matrix C. This is always equals to A is added to sum of two matrices. So in place of sum, you can replace it by product. So what you will get, AB of C is equals to A of BC. What does it mean? If we are having three matrices A, B, C, A, B is multiplied first, you will get the product. And if this product is being multiplied with the matrix C, or B and C are multiplied first and this product is multiplied with the matrix A, in both way you will get the same result. And this property, you know, is known as associative property. But look at here, we will multiply A, B and C, so their order should preserve, or the basic condition which must be satisfied before multiplying any two matrices. Look at here, if A is a matrix of order n, M by N, then we are multiplying A with B. Then order of B should be N by, say, P. B is multiplied with C, then order of C should be P by, say, Q. Right? Are you getting the difference? Because this is the requisite condition for product. Columns of A should be equals to rows of B to find out AB. To find out BC, columns of B, that is P, should be equals to rows of C. So this is how we will define the orders of A, B and C. Then we can check whether this property is satisfied or not. So matrix multiplication is very much associative in general, right? The next property is what? If A, B, C are three matrices of order M by N, N by P and P by Q, as we have taken in the last property, then this property is satisfied, right? The matrix multiplication, this is known as distributive property, and the matrix multiplication is distributive with respect to addition of matrices, and this is known as distributive law of matrices. So this is very simple. If a matrix A is multiplied with the sum of two matrices B and C, what does it mean? If A, B, C are three matrices, you are adding B and C. if this addition is multiplied with the matrix A, then this is always equals to AB plus AC. In the second way, if A and B are added first, and this addition is being multiplied a matrix C, then it is equals to AC plus BC. This is a very famous property, and this is known as distributive property. It is satisfied by the matrices. The next property is what? Let A be a square matrix of order n and I is an identity matrix of the same order, then A into I is equals to A or I into A. This is the property of an identity matrix. I have told you identity matrix is a matrix. When any matrix is multiplied with it, the matrix should remain the same. This is the property of identity matrix. Clear? Identity matrix is a matrix. When any other matrix is multiplied with it, the matrix remains the same. So A is a matrix, I is an identity matrix. I will be treated as identity matrix. If A is multiplied with I, A should remain the same. So A into I is A or I into A. In both ways, it's true. So I is called an identity matrix. The next is if the product of two matrices is a zero matrix, then it is possible that none of them is zero matrix. That is, if AB is equals to 0, then A is not equals to 0 and B is not equals to 0, where 0 is a null matrix. Oh, very good. It's a very good property which is possessed by the matrices. In the very beginning, I have told you that matrices behave almost like numbers, but there are few characteristics or few properties that is possessed by the numbers, but they are not possessed by matrices. On the other hand, there are few properties which are possessed by the matrices, but they are not possessed by the numbers. For example, in case of numbers, the division is always valid. Means you can divide a number with any other number, no issue. But in case of matrices, division is not valid. It means a matrix cannot be divided by any other matrix. Number one. This is the property which is possessed by the numbers, but it is not possessed by the matrices. And in the same way, if you reverse the case, the property number 5, this is the property which is possessed by the matrices, but it is not possessed by the numbers. What we know about numbers, whenever two numbers are multiplied together, it's a very fundamental rule of arithmetic. If the product of two numbers is 0, then it shows that any one of them must be 0. Clear? If the product of two numbers is 0, then it is mandatory or it is necessary that at least one of the number must be 0. Means 2 into 0 you will get 0, or 0 into 2 you will get 0. The product of these two numbers will be 0 only if any one of these two is 0. Either this case or this case. 2 into 5, both are non-zero, you can never get as a 0. So this property is valid for the numbers. If the product of two numbers is 0, then at least one of them should be 0. But here in matrices, if we take two matrices A and B, their product is 0, then this implies that neither A is 0 nor B is 0. Are you getting the meaning of this property? What does it mean? It simply refers to if we take two non-zero matrices, non-zero matrix. Zero matrix, you know, zero matrix is a matrix whose all entries are 0, right? It is also known as null matrix. So what this property refers to, in fact, it refers if we take any two non-zero matrices and if we multiply them, the product of these two non-zero matrices may be a 0 matrix. This is what this property refers to. And you think it very carefully again, this property is not possessed by the number system. If the product of two matrices is a zero matrix, then it is possible that none of them is zero matrix. That is, if AB is zero, AB means the product of two matrices is zero, then A is not equals to zero and B is not equals to zero. So simply it directly implies that we can have two non-zero matrices whose product we can get as a zero matrix. Let us understand this property by this example. This is the matrix A and this is the matrix B. Of course, A is 1 minus 1 minus 1 1, it's a non-zero matrix. B is 2 2 2 2, it's also a non-zero matrix. Now see what happens when we find out the product AB. Let us try to find out the product AB. AB is equals to what? 1 minus 1 minus 1 and 1, and B is 2 2 2 2, right? So the product AB. See, this is a non-zero matrix. This is also a non-zero matrix. I have told you what is a zero matrix. Find out the product. The product is what? 1 into 2 is 2. Minus 1 into 2 is minus 2. So 2 minus 2. Multiply the first row with the second column. 1 into 2 is 2. Minus 1 into 2 is 2 minus 2. Again, same. Take the second row. Minus 1 into 2 is minus 2. 1 into 2 is 2. Again 2 minus 2. Minus 1 into 2 is minus 2. 1 into 2 is minus 2. Again 2 minus 2. So what you will get here as 2 minus 2 is 0. This is 0. This is 0. So see, A is a non-zero matrix. C, this is a non-zero matrix. B is also a non-zero matrix. But if we multiply these two non-zero matrices, their product is coming out to be a zero matrix, right? This is a very interesting property possessed by the matrices. The next property is what? If A and B are two matrices such that AB is equals to 0, then it doesn't imply that BA is equals to 0, where 0 is a null matrix. These properties are actually very important, right? You people should remember or understand. I will use the word understand rather than remember these properties, because these properties will help you a lot during the solutions of the various questions. Okay. So this is property 6. If A and B are any two matrices such that, what does it mean? A and B are any two matrices. If we multiply AB, the product of these two may be 0. But if the product of the two matrices AB is 0, then it does not always imply that the product BA is also 0. Are you getting the meaning of this property? If we take two matrices A and B, we find out the product AB first. AB is a zero matrix. Then it is not necessary that BA is also a zero matrix. This is what this property refers to. See, this is the matrix A and this is your matrix B. Now, as usual, find out the product of these two matrices, that is zero matrix, right? A, 0 into 1 is 0, 1 into 0 is 0, so you will get here 0. See, 0 into 0 is 0, 1 into 0 is 0. Now take the second row, 0 into 1 is 0, 0 into 0 is 0, this is also 0. Second row with the second column, 0 into 0 is 0 and 0 into 0. Total everything is 0. So this is a null matrix. The product AB is a null matrix, right? So this is a 0, right? But if we reverse the order, BA, then this product C, take the first row 1 0 multiplied with 0 0, 1 0, 1 into 0 is 0, 0 into 0, this is 0, 1 into 1 is 1, 0 into 0 is 0, so this is 1, this all 0. So this is not a zero matrix. Means we can take two matrices A and B, of course they are non-zero, and the product of the two matrices AB is coming out to be 0, then it never implies that if we reverse the order, that is the product BA is also 0 as shown by this example, right? The last and the next property is what? If A, B and C are matrices such that AB and AC are defined. What this property refers to, this is also a very important property. If we take three matrices, say A, B and C, right? ABC are matrices such that ABC are such matrices so that the product AB is defined and the product BC is also defined. It means we can multiply A with B. The condition for the multiplication must be satisfied. We can multiply B with C. So naturally the condition for the multiplication of BC should be satisfied. ABC are matrices such that AB and AC are defined. Then if they both are equal, AB is equals to AC, AB and AC, not BC, AB and AC, and anyhow they are equal, AB and AC are defined, we multiply, we find out AB and we find out AC, and fortunately AB and AC are coming out to be equal. If AB and AC is equal, then this does not imply, be careful, B is equals to C, right? This property is also a very famous property, and this property is known as cancellation law, right? This is also a very good property. This property is known as cancellation law. So what does it mean? If we take any three matrices A, B and C, we find out the product of AB, then we find out the product of AC, right? And fortunately, both AB and AC are same, are equal. So if AB and AC are equal, it never implies that B and C are also equal. Why we are emphasizing on this? AB is equals to AC, then it never means we cannot cancel A with A in this equation, right? So this never implies that B is equals to C. Never implies, be careful, does not imply B is equals to C, right? See by this example, let us take the matrix A is this and B is this and C is this. We have taken these three matrices, right? Find out the product AB. Find out the product AB. I think you can very easily find out the product. AB is what? AB is simply, what is A? A is 0, 0, 1, 0. And what is B? B is 2, 0, 0, 0. Right? What is AB? AB is C. 0 into 2 is 0, 1 into 0 is 0. You will get here 0. Take the first row with the second column of the second matrix. 0 into 0 is 0, 1 into 0 is 0. So this is also 0. Right? Now, the second row is 0. So anything is multiplied with 0, you will get 0. So this is 0, this is 0. So AB is coming out to be 0. Right? Now, find out AC. AC is what? A is as usual 0, 0, 1, 0. And C is what? C is 3, 0, 3, 0, 0, 0. Right? Now find out the product of A and C. As usual, AC will be what? AC is 0 into 3 is 0, 1 into 0 is 0, you will get 0 here. 0 into 0 is 0, 1 into 0 is 0, and the whole row is 0, so you will get the product as 0. AC is also coming out to be 0. So what we obtained here, AB is 0, AC is 0. So naturally we conclude that AB is equals to AC, right? This is AC and this is AB. Both are same. But look at B and C. B is equals to what? B is the matrix 2, 0, 0, 2, 0, this is 2 0 0 0. This is the matrix B. And what is C? C itself is given as 3 0 0 0. AB and AC both are same, but B and C are completely different. So whenever we have three matrices A, B and C, and AB is always equals to AC, then it never implies that B and C will also equal. And finally, we can also see that positive integral power of the matrix. What does it mean? It means if A is a matrix, if A is multiplied with itself A, so we will get A into A square. The integral power of A is 2. Likewise, A square is multiplied with A, you will get here A square into A cube. Similarly, A cube is multiplied with A, you will get here A cube into A4. Or in other way, we can write A4 is equals to A into A into A into A. And how many times a matrix is being multiplied with itself, we denote it by its integral power. Let A be a m by n matrix. By definition of the matrix multiplication, the product A into A, see this, the product A into A is defined only if m is equals to n. Means both are, A is a square matrix and the product is denoted by A square. So whenever the matrix is being multiplied by itself, the product of the matrix with itself, you will get the power or the integral power of the matrix, that is denoted by A square. So naturally, if you are getting A square, you again multiply A square with A, you will again get A raised to the power 3. If you are having A raised to the power 3, again multiply with A, you will get A raised to the power 4. So doing this way, we can have A raised to the power n means what? A into A into A. If n matrices, or if a matrix A is being multiplied n times, then we will get its power as A raised to the power n. Is it clear? So this is how we can define the positive integral power of any matrix. And simply, what does it mean? A4 simply refers the matrix A is being multiplied by 4 times. Right? If we are having to find out A raised to the power 100, this means the matrix A must be multiplied by how many times? Of 100 times. Right? So this is all about what we have discussed. So students, thank you very much. I should stop it here and we will continue in the next lecture. Thank you very much.